In exercise 14, we're given a system of equations. We're given 4 choices and asked which of the systems in the choices has the same solution as the system given in the problem. There are several ways you could approach this problem, and let's take a look at a few of them. Some are more simplistic than others. One possible way is to take the system of equations given in the problem and to solve it. You could use any one of a number of methods, substitution, elimination, or graphing, and you'll find that the solution is the point 3, 5. In this exercise, I used elimination, but any of those other options would have worked just fine. Now, one possible way to proceed is to solve the systems in choice 1, 2, 3, and 4 and see which of those systems has the same solution. But that's very time-consuming. That's not the easiest way to go about this. If you think about what we learned this year, we learned that a solution means that it makes the equation true. It's the x and y values that make an equation true. And the solution to a system is the pair of x and y values that make both equations true simultaneously. We can use our values x equals 3 and y equals 5, along with substitution, to see which system of equations is true to find our answer. And so we do that. We substitute in 3 for x and 5 for y into all of the equations given in the choices. If both equations are true, then the system is true. And when we do that, we notice that choice 2 has both equations true. 16 equals 16 and 8 equals 8. That means choice 2 has the same solution as the original equation did. And so we found our answer to this problem without having to go through and solve 4 more systems of equations. That's a great way to go. Now I want to point out one more thing. When we did our original work, when I used the elimination method to solve the system of equations, I want you to notice something that happened. Notice that the 2 equations that I have in my second step show that they completely match the equations in choice 2. It's an equivalent system. If I had noticed that the equations I wrote matched the equations given in choice 2 right there, I would have had my answer. Which means we can think about how we might manipulate the original equations to match the new ones. That's a slightly more advanced idea, but it's something that you could do to determine the answer to this problem. Take a look. If I look at choice 1, on the left side I have the original system, and on the right side I have the choice 1. Let's see what I might have done. Well, it looks like they tried to multiply the original equation, the second one, by 2. But they forgot to multiply the 4. It should have been an 8. So choice 1 is not equivalent to the original system, so it's not the answer. It will not have the same solution. Choice 2, it looks like they multiplied the second equation by 2. That gave us 6x minus 2y equals 8. Those are equivalent equations, which means choice 2 will have the same solution. If we look at choice 3, we can see the difference lies in the first equation. It looks like they tried multiplying by 1/2 so that 2x would become x, and 2y would become y. However, they forgot to multiply the 16 by 1/2, which means this system is not equivalent. It will not have the same solution. And I look in choice 4, and I notice that it looks like they multiplied the top equation by 3, the bottom equation by 2. However, it should have been 6x minus 2y equals 8 in the second equation, and so they're not equivalent. They don't have the same solution. That means choice 2 is the correct answer. It has the same solution as the original systems of equations did. In exercise 15, we're given a table of values that shows a function f. The inputs are x, and the outputs are f of x. They ask which equation is represented in this function. One possible way to solve this problem would be to take each of your equations and put them in your graphing calculator and look at a table of values. Which table of values matches the table given in the problem? When we look closely, we see that the table for function 3, f of x equals 2 to the x plus 1, matches the table given in the problem, which means the answer to this problem is choice 3. In exercise 16, we're told that John has some nickels and some dimes in his pocket. We're told that these nickels and dimes total $1.25, and that he has 4 more nickels than he does dimes. We want to write an equation that can be used to find the number of dimes in his pocket. Let's begin by organizing the information. We know that John has X dimes. Dimes are worth 10 cents each. He has 4 more nickels than he has dimes, and so the number of nickels is X plus 4. Nickels are worth 5 cents each. The total value of his coins is $1.25. And so we have X dimes at 10 cents each, X plus 4 nickels at 5 cents each, and that equals a total value of $1.25. Now let's write our equation. 0.10 times the number of dimes plus 0.05 times the number of nickels equals $1.25. Look carefully at the choices, and you see that this equation isn't exactly there. But we know that we can reverse the order of terms connected by addition by using the commutative property. And so we can reverse it, so 0.05 times x plus 4 plus 0.10 times x equals $1.25. Choice 2 is our answer. In exercise 17, we're given a function, f of x equals 1/3 x plus 9, and asked which of these statements is always true. Let's begin by looking out a graph, and let's zoom out so that we can see a lot of the function, because that tells us a better story of what's going on. If we look at the graph, we see in exercise 1, the claim is f of x is less than 0. F of x represents the outputs, the y values. Are the y values always negative? Let's look at the graph. We've highlighted the region where the y values are negative. Are all of the y values negative on the graph? It doesn't look like it. It looks like there are some y values that are positive where it's above the yellow area, and so choice 1 is not correct. Choice 2 says f of x is greater than 0, meaning the outputs are greater than 0 or positive, the y values. Are the y values always positive? Not according to the graph. We can see on the left-hand side that there's some y values that go into the negative part outside of the yellow shaded region. You might not see this if you didn't zoom out on your graph, so if you're using a graph to solve this problem, it's important to zoom out quite a bit so you can really get a good picture of what's happening. Choice 3 and 4 involve the x values. If x is less than 0, then f of x is less than 0. What that says, if the inputs, the x values, are negative, which is on the left side of the red line on the graph, then the y values, the outputs, are also negative. But we can see that there are some points on the left-hand side of that big red line on the graph where the y values are positive. And so choice 3 is not correct. How about choice 4? If x is greater than 0, then f of x is also greater than 0. If the inputs are positive, the outputs are also positive. The x values and the y values are both positive. Is that true? Look on the graph at the red line on the right-hand side of it. Are the outputs always positive? Yes, they are. And so choice 4 is always true, and that's our solution.